All right. So we were looking at passives the other day, and we started looking at this spiral inductor, and we know that the spiral inductor works more or less just by running current, time varying current through the metal, and linking flux between different elements of the winding, which increases the overall inductance using the mutual inductance that comes from that flux linkage. We were looking at the cross section, and we note that we build the inductor primarily, at least the asymmetric inductor, with an inward winding spiral, and then when we get all the way into the inner part of the spiral, we have to make a crossover. So we showed, if we look at the cross section of this inductor, we have some upper metal. We go through a via, we go through a lower metal, and that lower metal has also some inductance, some partial inductance, some resistance. And then ultimately, it also is going to have some capacitance as well, because the metals are separated by insulators. And indeed, you'll even have some capacitance down to the substrate. And so we can make a circuit model of this structure. It is generally, or most of these that we can integrate on chip are generally going to be electrically small, which means that we can approximate this with lumped elements. And the common lumped element model is called a 9-element lumped element model. And you can see that we have, some inductance L spiral that represents the inductance from the spiral. We have some metal, R metal, which represents loss due to finite conductivity of the metal. We have that bridging capacitance, which comes from primarily from this overlap capacitance. But there's also a little bit of capacitance between each section of the winding. And then we have oxide capacitance, and RSI is representing the resistivity in the silicon. And then there's this CSI. Now, this is not usually a physical parameter. CSI is just modeling the fact that the substrate resistivity has some frequency dependence upon it. And so you're adding a parallel capacitor to give it that frequency dependence. All right, so let's recap that. We can let's go back and label our inductor a little bit better. So you might have port 1 here and port 2 coming out over here. So here's our inductor model with port 1 and port 2. And, just what I said, this is partial self-inductance.
I wonder if you can avoid the dark blue on black, because that's very difficult to read.
Oh, sorry.
Can I adjust the light?
Yeah, you can adjust the light. No, we don't want to go to sleep. This is not exactly EY stream. Okay. Now, through the magic of digital ink, let's change the pin color. There we go. That's not one of my pens. I like that color. It's pretty good. I should set that somewhere. Let's see. I don't need a highlighter, do I? What I need is a fuchsia pen. I'm gonna delete this. Just add a pen. Pen. With that. Yeah. It's awesome. It's good stuff.
It really sounds like you're trying to convince yourself.
I might be. Not sure about that. It looks like we're doing circuit design in Miami. This is very Art Deco. All right, so we have partial self-inductance from the metallization. We have our R metal, which is ohmic loss from the metal. We have C bridge, which is that capacitance due to metal overlap, primarily. And then we have C ox, which is the capacitance to the substrate. R silicon is, or RSI is representing ohmic loss due to eddy currents. And C silicon is a fitting parameter. I'll say it's quasi-physical. I say quasi-physical, it's really non-physical. They're just really trying to fit the substrate loss with respect to frequency, but there is in practice some capacitance from the top of the substrate to the bottom of the substrate. So we can say that it might be mimicking something physical. All right, if we use any real inductor, it has a self-resonant frequency. You know, what we expect with an inductor is that in general the impedance is going to increase with frequency, and it should be increasing linearly with respect to frequency. And in fact, you know, it should be doing so at 20 dBs per decade. So at low frequencies, L spiral is dominant. And then at high frequencies, the capacitance in the structure is going to dominate. This is mostly due to C bridge, but all the capacitors contribute. And since the capacitance is dominating, the impedance is decreasing at 20 dBs per decade. And at this center frequency, this is called the self-resonant frequency, or we'll abbreviate it SRF. This is the frequency where the inductor resonates just with its own parasitic. So the physical manifestation of that's required to make this inductor brings along all these parasitics and creates a resonance just by itself. And you know, we can approximate this and say that it's more or less equal to 1/2 pi times the square root of L spiral times C bridge. Okay, yeah.
Is it possible to use this past SRF? So when the C is kind of taking over?
Well, you can use an inductor past the self-resonant frequency, but it's not going to give you an inductive-like behavior. It's going to look like a capacitor. So, and because it's parasitic, it's not necessarily a well-designed capacitor. It would be a big non-well-designed capacitor. So we probably want to do something else. But yes, technically you can. We tend to have to model that. So, you know, one of the things with this model is it's this is just a one-stage model. If we want more accuracy, we can cascade sections of this together. You can think of this kind of like a mini version of the transmission line model from the telegrapher's equation. If we, you know, in that equation, if we have infinitesimally small sections, we approximate them, you know, as, you know, RLGC sections. We can cascade a bunch of these together and it makes the model more accurate across a broader range of frequencies. So mostly at higher frequencies above SRF, we just want to know what the impedance looks like because it might have some impact on the performance of the circuit. Like it might end up, you know, enhancing or suppressing a harmonic, for instance, depending upon the behavior. So we have to be aware of it. That's mostly what we're going to do. I realize this paper got small. Here we go. Okay, so for inductor design, your tools are pretty good at doing the design of the inductors nowadays. And we'll open up Cadence in a little bit and start looking at some of the passives. But you know, generally you can put in, you know, a parametric, some type of you know, parametric value for each of the physical properties of the inductor. So number of turns, spacing between turns, width of the turns, those kinds of things, and it will calculate what the inductance does. If you don't have a tool that does this, the way that we normally estimate inductance is to use the low frequency estimate, you know, based upon geometry. And there's a reference from Greenhouse that, you know, where they did this. And basically what they do is they boil every element down to a filament. So they take a, you know, a three-dimensional conductor and they, you know, pretend that it's just a single filament of wire, which is just a two-dimensional piece of wire. And that wire will have some partial self-inductance. And if you have a loop of these things, you can calculate the partial self-inductance for every segment, add them all together. You'll have some partial mutual inductance. You have to add that too. And these two papers show you how to do that. It was actually my master's thesis was coming up with a quick way to calculate these things. It was obviated by machine learning and all these other things. Okay. How do we make a capacitor? Well, we have a MEM capacitor. Oh, you know, let's get rid of this terrible dark blue. I like it.
Professor, can you also show us like how can we design transmission line inductors?
Well, I don't know that transmission line inductors makes a whole lot of sense. A transmission line is a physical element that has in both inductance and capacitance in a proportion that keeps the ratio of the voltage to current waveforms constant on the medium. We can, if you're asking how we make an inductor out of something that is not a spiral, is that more or less what you're asking?
Yes, sir.
That cut off. Was that right?
Yes, Professor. Yeah.
Okay. Sorry. Yeah. So every piece of wire has some partial inductance. And you know, it turns out actually that a piece of wire generally we can almost always approximate this as about 1 nanohenry per millimeter at DC. Doesn't really matter much about the size of the wire. Like I said, the estimates, we actually just boil everything down to a filament anyhow. So you get about 1 nanohenry per millimeter at DC. And so, you know, any piece of wire has partial self-inductance. So if you're making a transmission line like structure, you know, it might look like a microstrip, but you're just leveraging the fact that it has some partial self-inductance. That won't be a very big self-inductance.
Like a single line, right? It should be just a single line.
Yeah, it could be. So we call them, you'll see them in the literature called slab inductors.
Okay. All right, Professor.
But that's what they are. That's what they are. Yeah. Okay. Capacitors. On chip, we can make capacitors in a couple of different ways. The MEM capacitor is the primary way that we do it. MEM is metal, insulator, metal. These used to be fairly popular on older RF processes, but they're kind of not in favor any longer because they're expensive to produce and they have poorer performance at higher frequency. And the way that they make these is you take, you know, maybe the same two pieces of metal that we looked at before. So we'll have some top metal and some bottom metal. And then they'll make this mezzanine layer. And they'll strap it down to either the top metal or the bottom metal. Usually it's the bottom metal with a bunch of vias. And then you get a capacitance, you know, between the two plates. So it's just a parallel plate capacitor. And, you know, essentially because C is equal to the permittivity times the area divided by T, they increase the capacitor density by decreasing T, where this distance is T. All right, so that's the cross section. If we look at it from above, we see something like that. Yeah.
So you're saying, when you said they changed the T, that's not like, I mean, it's fixed for one process, right?
Yeah, that's fixed by the process. You can't physically change T. The process engineers will determine what they want the capacitor density to be.
And what does the mezzanine mean? I know I've heard that used in different contexts. What does it mean here?
It just means a layer between two layers.
Okay.
It's like the you know, between the floor seats and the balcony. Got a mezzanine in an orchestra. Look, the tools that we use to design these things are called cadence, and they're all, you know, they're virtuoso, maestro, you know, so it's not
ADEL.
well, ADE is, you know, I don't know what that stands for, but
So normally, I guess.
That is analog design environment.
I was teasing. I know that it means analog design environment. I just didn't know. I can't rapidly turn it into a musical analogy.
My question was essentially like, the routing is going to be normally limited to whatever the top end requirement is. We're not allowed access to the mass name without having to do capacitors. Or would it be something that
you can technically, so I mean, there are always a ton of process rules. You can technically use almost any metal layer. You just have to use it within the rules of the process. And normally this layer will have a lot of rules associated with it in terms of tying the structure down, because as they build the process up, charge can build up on any metal layer, and then when they connect it, you know, to other metal layers, there might be a discharge path to ground. So you can have nasty ESD events, and the thinner the oxide, the lower the critical E field that might cause that oxide to break, right? So there are lots of rules associated with doing it, but yeah, you can use it. It's the thing I should note is it's a very thin metal. almost always this metal it's maybe got the same thickness of the metal one layer, so it's lossy. So you wouldn't want to do anything like route in it. Yeah. All right, we have a circuit model for a capacitor. It's a little bit simpler than the inductor. In fact, we might count this and say that this is a 7-element model. Obviously, the big difference between the inductor model is we don't have that bridging element because the capacitor itself kind of is the bridging element. And we don't worry as much about fitting the frequency of the substrate with this particular model, like we did in the other one. You've got, if we look at the model, CMIM basically is that C calculation, epsilon times A divided by T. L metal, again, every piece of metal can be approximated as a filament. So every piece of metal that's conducting current has some self-partial inductance. R metal represents metallization or ohmic loss in the metal. C sub is the capacitance to the substrate. So more or less, this stuff. And RSI is the resistivity in the substrate. All right. I mentioned that these things don't do very well at high frequency. We tend to, once we get much above, say, 10 to 15 gigahertz, they start to be pretty poor choices for capacitors. And in fact, I haven't seen a MIM capacitor in any process past 55 or maybe 40 nanometers. At least I haven't used one in any of those processes. This is the other type of capacitor. It's called a VN cap, or vertical natural cap. Sometimes we also call it a finger capacitor because it's kind of like, imagine interdigitating your fingers like so. Of course, they can't touch. They have to, be insulated from one another. All right. So generally here, the fingers are increasing the coupling area. You could theoretically just, bring two pieces of metal close together, but when you do this interdigitation, it increases the total area of the capacitor. Okay, and normally we're gonna put multiple layers together to increase the capacitance density. So we like to talk about the capacitors in terms of the density that they provide. The MIM capacitors, you typically get something like 1 femtofarad per micrometer squared. The vertical natural caps, they can get up, towards 1 femtofarad per micrometer squared. But you have to stack a lot of metal layers in order to do that. One other thing about the MEM caps that I didn't mention is sometimes processes will have a dual MEM cap where they have 2 mezzanine metal layers. And again, they're just really trying to decrease the thickness between the between the 2 metal plates, really increasing the capacitance density. And in some of the processes that I've seen, they can get about 2x the density for a dual MEM cap compared to a single MEM cap. All right, our circuit model for this one is similar to the MEM cap. You should ask, why do we care about making a circuit model? We can just do a full wave EM simulation. nowadays. Yeah, it's time. It takes a lot less time to simulate if we have a model. And the other thing is that it used to be that transient-based simulators would object severely when you tried to put an S-parameter-based model into them. Nowadays, most transient simulations will handle S-parameter models fairly well. I see disaster in the future.
Now can you bring water?
For your water.
Yes.
Start with all right. All right, we have a couple of other structures that we can make in terms of electromagnetics. So, one would be a spiral transformer. Another would be the one that Salakin asked about earlier, which would be the slab inductor. And of course, we can also make transmission lines on chip. Now, for the most part, when we're on chip, we tend to want to use lumped element components because transmission line based components are things where we're using some large fraction of a wavelength that even up to relatively high frequencies, those components can be quite large on chip. So we favor using lumped components where possible. And generally it is possible. But we will see as we get towards 100 gigahertz, we'll start to see transmission line components. And Peter had a question.
Yeah. Sorry, I missed that VN cap. Is that a cross section or top down? That was top down, right?
That's
Yeah,
top down.
top down,
Yeah,
yeah.
yeah. And normally when you make these multi-layer, you'll have one layer like this, and you'll rotate and every layer. That way, it just increases the density of the cap. You're just trying to increase the cross-sectional area where one metal is overlapping with another metal.
So if this is a top-down view, would that mean there are views in between every single figure?
If you're connecting to lower metal layers, yeah. We'll try and open up a layout or two and show you what they look like. All right. So we have a tool that's integrated into Cadence called EMX. So we can generally solve for the primary parameters for any of these passives using an electrostatic approximation, meaning for inductors, I can use that greenhouse approximation if I want to. And that will tell us, roughly how I should size the device. And then I can draw it and then run a simulation. We don't want to rely on the simulator to design for us because simulators are costly in terms of licenses. Now, I will say, while you were students, you get virtually free CAD licenses, but that's because the CAD companies are largely like drug dealers. They're trying to get you hooked right now, so that when you go to your companies later on and are working, you demand to have a particular vendor, so that because you know how to use it. Anyhow, it works with everything. So yeah, get them while they're young. That's right. If we look at the impedance of a cap, it's kind of the exact opposite of the impedance of an inductor. You'll have a reduction in impedance of 20 dBs per decade with increasing frequency, while the capacitance is dominating. And then at some frequency, you'll have a self-resonance, and then the inductance will dominate. So this looks like a C, this looks like an L. And there's a self-resonant frequency. Now with the cap, the self-resonant frequency tends to be a lot higher. because there's a lot smaller self-partial inductance associated with the cap. Caps are smaller. Okay, and I didn't note it here, but I gave us some other passive structures. We can also generally make resistances if we need to. We can make resistors in CMOS processes out of metal. Those tend to have a low resistor density, but we can also make them out of wells. So we can put a well down and either drive an implant into the well, which will change the resistivity, not implant the well, which will change the resistivity, or we can make resistors out of polysilicon, and they can dope the polysilicon, I call it saliciding it, or not dope it, so they can change the resistivity of the polysilicon also. Now, as you go into FinFETs, which we're not using right now in this class, but as you start to look at FinFETs, the number of resistors starts to decrease. They typically have to do something like poly resistors, and that's about it. So. Okay, now let's talk about losses in matching networks. For the most part, these are going to be dominated by inductors. Inductors are big. The eddy current losses can be pretty substantial, and also because the metal is winding in on itself, even the metallization winding losses can be relatively substantial for an inductor. So typically, these are going to be dominated by inductors. And the analysis that we're going to look at here is relevant, pretty much for any lossy passive network. So let's assume we have a 2-element matching network, and we're going to convert the antenna impedance to an optimal impedance for a power amplifier. Now, we haven't started talking about PAs. We'll actually probably maybe get there today, maybe start on PAs on Monday. But the R-opt for a power amplifier in CMOS tends to be quite low. So let's talk about R-opt. What is it? All right. And the process that we're using, if you cascode transistors, you might be able to use a supply voltage that's equal to 2 volts. Supply voltages in CMOS tend to be labeled VDD for the drain supply. I tend to forget I do have some folks that are not pure circuits nerds like myself. So VDD is the drain supply voltage. Let's say we want an output power that is equal to 1 watt, and we want to operate in a Class A mode. Now, Class A is the mode for amplification that most of us think of. It means we put a sine wave in, and the transistor conducts for a full sine wave at the output. All right, so what is R-opt? Well, you can show that the power out of a Class A PA is equal to VDD squared over 2 times R-opt. Therefore, we can just invert this equation to find R-opt. And you'll find that it's about 2 ohms in this particular case. All right, so quite tiny. What's the Q of the matching network? If we're just transforming from 50 ohms to 2 ohms, what's the Q?
I want to hear what his answer is.
Oh, wait, are you answering the question?
No.
No? What's the Q of the matching network?
I have no idea what you're talking about.
I don't know that Rohit does either. Do you?
Is it square root of 24?
Yeah, it'll be square root of 24. So the Q is
A picture in meters image.
all right, I'm gonna have to edit my video now. and pretend that this didn't happen. Hey, can you? All right, we'll take a picture later, I promise. Okay, so Sean got that right. Q of the network is square root of R big over R small minus 1. So square root of 50 over 2 minus 1. I'm just going to say that that's approximately equal to 5.
So I can see that the difference between the switch and PC region
Yes.
what
All right. Okay, so we're going to do this impedance transformation. Ultimately, what we want to do for a power amplifier is we want to present 2 ohms to the transistor, and that means that when we look into the matching network, we want to do the transformation such that it makes 50 ohms look like 2 ohms. Here we have a low pass downward transformation from the perspective of the 50 ohms to get that 2 ohms. Now, if we look at these components, we've drawn this as an ideal network, but in reality, this inductor, looks something more like this. Now, we could add all the other elements of the 2-element model, but really we just want to model it as being an inductor with some loss. And we can model the Q just of the inductor. So this is not the Q of the network. The Q of the network we just found, but the Q of the inductor is equal to XL over RL, or omega L divided by RL. And our capacitor we can model as lossy as well. So here I'm going to model my capacitor with a parallel network. It's usually best to, if we have a series component, to use a series equivalent model, and if it's a shunt component, to use a shunt equivalent model. So here we have C and we have an RC, and QC is equal to RC over XC, or it's equal to omega C times RC. All right, so if I just replace that figure, the prior network, with the model that we just made. And now we can calculate the power that's available at the source, the power that we deliver to the parallel resistance RP at the load. And we know that the power available from the source is equal to 1/2 IS squared times RL. And the power dissipated in that parallel due to the capacitance is P parallel 1/2 VP squared over RC. All right, so we can figure what the loss is just due to the inductor. We're going to equate it and say, ultimately, basically the power, the power throughout the network needs to sum to 0. So we can say that P loss in the inductor is equal to 1/2 IS squared times RL. And we're going to replace RL with its value according to the Q of the inductor. All right, so all I've done is substitute for RL according to the Q equation that we looked at earlier. And if we do a little bit of manipulation, we can even, factoring in that the Q of the network is dependent upon both RP and RS, we can make one more substitution and find that this is actually equal to Q network over QL times the power available from the source. We can do a similar thing for the loss in the capacitor. This is 1/2 VP squared times omega C over QC. This is equal to Q network over QC times PP. So we're just using these three equations up at the top and doing some algebraic manipulation to get these. All right, so the power that we deliver to that load ultimately has to be equal to the power available from the source plus the loss in the inductor and the loss in the capacitor. And if we find the ratio of the power from the source, of power available from the source through the divided by the power delivered to the load, we'll find the efficiency of the network. And the efficiency here is equal to 1 minus Q network over QC divided by 1 plus Q network over QL. Now this equals 1 if Q network is equal to 0 or QC and QL are equal to infinity. So this is just telling us that if we want to have a lossless network, we can get it one of two ways. We can have lossless components. We don't lose any power in an inductor or a capacitor if they have no loss. Or we can make the quality factor of the network very small. Now that implies that the bandwidth of the circuit would be very big. With that two-element match, though, remember, we don't have any control over the quality factor in the network, and practically what we can do on chip is really, quality factors in the range of, 2 to 5, something like that. If we start trying to make the quality factor too low, what happens is we need to add extra elements, and adding extra elements adds loss. All right. Typically, the quality factor of an inductor on chip is in the range of 10 to 20. Interestingly, when the field of RF integrated circuits on CMOS started, the Qs were in the range of maybe 2, if you were lucky, to 3. Come a long way. The quality factor of the capacitor is much higher, typically in the range of 50 to 100. We can generally assume that the quality factor of the capacitor will be larger than the quality factor of the inductor. There are some cases where that might not be the case. For instance, if we're using MEM capacitors at very high frequency, then we have loss in the thin film from the MEM.
Deborah had a message.
Okay, well, we'll check. That's from Mama. We'll check it in a minute. All right.
Yeah.
If we assume that the quality factor of the capacitor is much bigger than the quality factor of the inductor, then our matching network efficiency for this matching network topology becomes something like QL over QL plus Q network. So here we're just assuming that QC is completely dominated by QL. Just to give you some context for what this means, if the network quality factor were 5 and the inductor quality factor were 10, so kind of the network quality factor that we just calculated was approximately 5, and an inductor on the low end of the quality factor range, we would see that the efficiency of the matching network would be 67%. course, you can directly convert this to dB, just take 20 log 10, and you'll find what the loss of the matching network would be in dB. If, on the other hand, we increase the quality factor of the network even more, so let's say we were trying to squeeze even more output power out of the power transistor, that means we need a matching we need a transformation that's even bigger. Then we'll have a higher Q. If we had the same quality factor component, 10 for the inductor, the efficiency of the network would be 50%. So our choices in topology play a pretty significant role in terms of the loss that we're going to see. All right, now we can change the order of the matching network. I'm not going to go through the derivation again, but we can have, for instance, an upward impedance, low pass upward impedance transformation. Or we can have, a downward high pass or an upward high pass. Depending upon the topology, the efficiency of the network changes just a little bit. It's really, is the inductor in series or is the inductor in a shunt configuration? So this network is our another low pass. What would we say is the impedance when we look? Is the impedance going to be higher or lower than RL?
Higher because you had to add a series.
It should be higher impedance.
Yeah, it's higher. So we have the transformation from the perspective of RL is always going to be increasing because we're adding a series element. From the perspective of where we are looking into the circuit, we're adding a shunt element, so that's going to be reducing the impedance. So it has to start out higher. So R looking in, where R is greater than RL. You can go through a similar derivation, but ultimately what we care about is what is the result. Efficiency of the network will be 1 minus Q network over QL. Yeah. Over 1 plus Q network over QC. I should actually link to this derivation. I use it for RF, but it was actually done from a professor at MIT named Dave Peralt, who was doing it for power electronics. Turns out it works still. All right, so we can, if we work from this side, going in this direction, we can say that the efficiency of the network would be equal to 1 minus Q network over, over QC divided by 1 plus Q network over QL. If we go from this side of the network, the efficiency of the network would be equal to 1 minus Q network over QL divided by 1 plus Q network over QC. I could have drawn the other two exactly the same way. Working from one direction, you're going to have one efficiency. Working from the other direction, you're going to have the other efficiency. All right, so we've used so far matching networks that might have more elements than we have in an L match. What happens if we have more than one section? Well, we can cascade L matches. So we figure out what the efficiency of one section is, then we figure out what the efficiency of the other section is. For those things like the pi network, remember we have an L network looking in one direction and an L network looking in the other direction. So we can just we can when we calculated the values for the pi network, we did that thing where we found the intermediate resistance. We can split up the network just like that, find what the loss is for each section, and we cascade them. So for instance, if we want to find the total efficiency of a matching network where we have n matching sections, then the total efficiency is just equal to H1 times, eta 1 times eta 2 times eta n, or we can say that this is the product from I equals 1 to n of eta of I. All right. All right. Any questions on that? Yeah.
So this heavily impacts the efficiency in terms of like maximum consumption.
Yeah.
In terms of when we're doing like PA designs, would there be any even measurements that we can do to characterize your PA's performance, isolating it from this loss?
I mean, it's hard to do a measurement of the passive network just by itself. But oftentimes when we build a structure like this on a chip, if we really want to know, if we want to be able to isolate, what is the transistor giving us versus what is the matching network doing, we could build the matching network back to back, measure its loss, divide by 2, do something like that. So people do make calibration structures, but it's less common to do something like that because the area penalty is pretty severe. You can imagine just adding an inductor just for the sake of calibrating out the losses is not a good use of silicon. So we also will use EM simulations just to estimate what that is.
So are there any separate metrics you classified, Josh, about PA's efficiency without having?
Yeah, sometimes I give a talk on power amplifiers where where you're trying to equate the, what you can ultimately show is that the efficiency of a power amplifier, and we'll look at this in a few days, is equal to the efficiency of the topology. So a class A amplifier has a topology efficiency of 50%. Class B amplifier has a topology efficiency of 70.5%. And then you can calculate what the loss is in the matching network. Your efficiency would be the product of those two things.
Yep.
And if you really want to go a step further, technically, when you present an impedance to the transistor itself has some impedance. And so in a linear power amplifier, you get a current division. So you can also have an efficiency factor that's due to the current division in the network. All of those things cascade, and that's your total efficiency for the amplifier. So a class A amplifier starts out at 50% efficient before you do anything. So its ideal efficiency is 50%. When you add in a lossy matching network, which might have an efficiency factor of probably less than 50%, and you add in a current division because the output resistance of the PA is quite low, so your current division ends up being bad. It's not unseen to have class A power added efficiencies on the order of under 10% peak.
Yeah, another question.
Yeah.
On the previous slide or page, those two expressions you showed for the efficiency of the matching network in the at the top of the page here.
Mm-hmm.
That they're different for I didn't quite get that. It's different when you look going one way or going the other way.
Well, so if you look at the way I drew this, let's go back and look at the original network that we drew. Here, if I look at this, I'm calculating this going in the direction in this direction.
Yeah.
I could have started from the load and gone in this direction.
Yeah.
That is equivalent to what I was actually drawing here. This one.
So you're not at the top of the page. So under the high.
I understand. So I just, instead of drawing this figure twice, so I could have drawn this.
Yeah.
And then we could have calculated the loss going, in this direction or in this direction.
And the loss is different in those.
Yes, it'll be slightly different. So you'll note that in this, oops, what did I do? In this equation, the loss from, so this is the first one that we were looking at, which was the downward transformation from the load. The inductor loss is in the denominator, 1 plus Q over Qn over QL. And this one, the inductor is in the numerator, right? So depending upon whether we're going, whether we have an upward transformation or a downward transformation, basically what's going to happen is the coefficient, or the numerator and denominator are going to swap.
Okay, interesting. I just didn't
Yeah.
expect that to be just like those.
Yeah, no, that's a great question. I didn't explain that very well, but yeah, that high pass network, we can have either an upward transformation or a downward transformation. Depending on what direction we're going from, we're going to see a slightly different loss factor. Now, in any of these cases, the inductor is still going to dominate generally. So normally what we say is QC is very big. That means that the 1 plus QN over QC doesn't matter much. Or 1 minus QN over QC also doesn't matter very much. All right, so let's just look at a quick example of what we might expect, using some slightly different parameters. Oh man, even more colors. Purple. Ah. All right, where did my little selection thing go? Oh, there it is. All right, we'll just do. I went to University of Washington, so I like purple. It's a good color. All right, so again, this just for a simple 2-element match, let's assume that we want a class B power amplifier that's going to output 500 milliwatts from a supply voltage of 2 volts, and we're going to use a 2-element match. But we're on a Cadillac process that's giving us an inductor that has a quality factor of 20. Our capacitor is still 50. What's the total efficiency? All right, see if you can work with a neighbor and tell me what you think it is. I've laid out the rough map, order that you have to do the math. I'll give you a minute or two to head start.
Yeah, it is. It's hard. Over years.
My online folks can also be chatting with one another. I am conveniently telling you to ignore current division and knee voltage. So. Now, I realize that I didn't tell you this, but the optimum termination for a differential ended PA is 4 times the optimal termination impedance for a single ended PA. You get twice the voltage swing with half the current in each branch. So you need that piece of information.
Is it just
50 ohms.
Mm-hmm. We'll assume that the antenna is 50 ohms. Anywhere I don't tell you what the character, what we're driving, it'll be 50 ohms. All right, so carrying on, we find that the network quality factor is square root of 50 divided by 16 minus 1. Anybody that's had my analog classes in the past know that that innately just equals 2 to me. We're going to get into a simulator very quickly. My job is to get into a simulator with a smart value, or at least smart enough, and then refine. All right. So we're going to use a low pass down converting impedance match. The low pass down converting had a form of 1 minus Q network over QC over 1 plus Q network divided by QL. Oh, that should be square root of 2. There we go.
okay? That explains the whole.
All right, I do sloppy math, but not that sloppy. I mean, come on. Now, anybody that knows my opinion on this says that that's exactly equal to 1.4. All right.
There's no end to this man's madness.
1 minus square root of 2 over 50 over 1 plus square root of 2 over 50. And given that I just told you to approximate everything down to, 2 significant digits, I'm going to say that this is 0.93 or 93%. All right, not bad. Now, our total efficiency is the efficiency of a class B times the efficiency of our network times technically the efficiency of a current division. But I told you to ignore that. What happened? So I told you to ignore that. Now, we haven't quite learned this yet, so a little bit awkward, but you'll take it from me right now. Efficiency of a class B is 78.5%. Efficiency of our network was 93%. And that means our total efficiency is about 73%. Alrighty. Now, I don't know too many people that use this particular method of finding the loss in the matching network, just from the network, but I found that it works pretty nicely if you're doing, algorithmic approaches to design. So I like to make MATLAB and use it to optimize things before I get into a simulator. And this works pretty well. And one thing you might notice is that the differential amplifier gave us quite a big advantage there. We didn't talk about why, but we don't want to make very large impedance transformations. If we make large impedance transformations, that means that the network quality factor ends up being big, and having a big network quality factor with lossy components hurts us. So we'd like to keep the network quality factor as low as we can. Practically, differential amplifier is a good way to do that. Now, the challenge, of course, is that much like for the low noise amplifier, our antennas tend to be single-ended antennas, so we typically have to use a bail-in if in the output stage. So we probably won't use just a pure spiral. We'll use a bail-in. If we want to estimate the loss of a bail-in, we can make a compact model of the bail-in that includes its winding inductance. All right, now, any questions? We tend not to cascade a lot of matching networks together. Most of the time, the most number of components that you're going to see on an RFIC, unless somebody's trying to make an absurdly wideband amplifier, they might do something. There are things called distributed amplifiers, where they're cascading transmission line sections and trying to make a synthetic transmission line. Unless you're trying to do something like that, you're typically going to see 3, maybe 4 elements, usually 1 spiral and a couple of capacitors. There are exceptions to that rule, but that's mostly what you're going to see. By the way, everybody picked really great papers for their projects. I was looking through this going, I remember reading a lot of these papers. So yeah, it's good. I know most of those people, so it's also good. All right, so we're going to start talking about a power amplifier. So what is different about a PA than any other type of amplifier? So, low noise amplifier, for instance, well, it's pretty obvious. PA is designed to deliver a specific amount of power with high energy efficiency. A low noise amplifier is designed to deliver a lot of gain with low noise. We don't necessarily care about the absolute output power that it can achieve, just high gain, low noise. PA, we want high output power with low DC losses. Now, it's not to say that other parameters are not important, it's just that we're going to favor one. So, parameters like noise figure and gain are still important. So we still care about these things, just not as much. Why do we care about noise in a power amplifier?
Secondary factor.
We're not anywhere near the sensitivity of the amplifier. Why do we care about noise in a power amplifier?
Last stage, yeah, that's it.
Yeah, whatever I drive into the antenna is going to radiate, including the noise. So we still care about it. Okay, RFPAs are typically designed to drive into an antenna. We typically call them something different if they're not driving into an antenna. So we might have for instance, in wireline systems, they might be driving a 50 ohm impedance, like a transmission line, but they tend to call those line drivers or just drivers. They're doing a very similar thing though, so a lot of the design principles are similar. Although they tend to need to be very wide band, whereas our RFPAs tend to be very narrow band. So, yeah. Okay. Now, a couple of things about this, that are important. So our antenna can have widely varying impedance. If you've if you're ever wandering around and you had a spectrum or a network analyzer and you could tie it to your antenna and watch what's happening to it as you just move through the environment, it can be all over the place. You can be walking out on the drill field, or let's see, we don't have any metal and glass buildings on this campus, do we?
There's that, our
Yes,
second
building. That's all.
Yeah. All this hokey stone. Hokey stone's probably somewhat reflective. Anyhow, the bottom line is that you can be walking on the drill field in the middle of free space, or walking up next close to objects, and your antenna is going to interact with those things. And when it's interacting with something, its impedance is changing. Not only that, many of us walk around nowadays with our phone in our pocket and a Bluetooth in our ear. But in the past, we had to actually hold our phone up to our ear. That changes the impedance. So as we design power amplifiers, we tend to design them to work into 50 ohms, but the impedance of an antenna might vary across a fairly wide range of VSWRs. For low frequencies antennas, it could be 10 to 1. You might have to be able to survive working into a 10 to 1 impedance range.
1 minute from now. So you got 60
Oh,
seconds.
okay. So, I'll just wrap up there so that I don't get dropped. The last thing I'll say is that a power amplifier is a large signal circuit. The LNAs that we look at, we're typically talking about working for very small signals that are in the microvolt, millivolt range. PAs are going to be working in, they're going to be swinging across the full range of their outputs. So they're going to be swinging across multiple volts with, tens to hundreds of milliamps of current flowing through them. So they're large signal circuits. We have to think about them differently. All right, so we'll stop there. You can look for a homework that will involve LNAs tonight. I did make I forgot to update the date, but the solution, or the homework was due today. That means you have a 1 week grace period. You can submit it till next week, and there'll be a new homework posted tonight. Yeah.
Professor, you mentioned about the 10 to 1 impedance. It means VSWR.
So what you were saying, there's a homework due tonight, but I haven't seen it.
No, it was homework 2. It was due. It was. I forgot to update. That was due this week. I gave you all a week. I gave you all an extra week. Yeah.
Okay.
Yeah. Did you have a question, Puya?
Yes, Professor. You mentioned
Sorry, did you have a question, Puya?
Yes, please. Can you hear me?
Yes.
Okay. You mentioned about 10 to 1 impedance. It means VSWR or?
No, 10 to 1 VSWR.
Oh, okay.
Yeah.
Thank you.
Yeah, no worries. All right, I will drop everybody off now. Talk to you next week, or I'll be around campus as well.
Okay. See you.